This month, in the 6th episode of Tech Threads, we break down the AI market from edge to cloud with an outside-in view. I'm joined by two brilliant tech voices, Sally Ward-Foxton, the leading analyst for Edge AI and senior reporter at EE Times, as well as Ian Cutress, the semiconductor analyst and founder of More Than More and Tech Potato, which is a channel with over 100,000 subscribers. So we'll explore the tech shaping our world, from chips and AI to the emerging realities of design and infrastructure. Stay tuned.
Welcome to Tech Threads, Weaving the Intelligent Future, the podcast exploring the fast-paced world of technology. In each episode, we dive into the latest innovations in data movement, AI acceleration, and the transformative potential of chiplet technology. Join us as we explore the breakthroughs that shape the future of computing and hear from industry experts on what's coming next in the tech landscape.
Hello and welcome to the 6th episode of Biosystems' Tech Threads podcast. I'm Nandan Nayampally, Chief Commercial Officer. And today we break down the AI market from edge to cloud with an outside-in view. We decided to change the format a bit, and today I'm joined by two brilliant tech voices, Sally Ward-Foxton, the lead analyst and voice for Edge AI, actually, and senior reporter at EE Times, and Ian Cutress, semiconductor analyst and founder of More Than More and Tech Potato. Together, Sally and Ian host a TV-style video series, The AI Hardware Show, which will be entering its second season this year. So there we'll be exploring tech shaping our world, from chips and AI to the emerging realities of design and infrastructure. Welcome, Sally. Welcome, Ian.
Thanks for having us on the show.
Yeah, thanks, Nandan. Pleasure as always.
Great. To give our viewers a little bit more about each of our guests, Sally, being a senior reporter at EE Times, is one of the sharpest voices covering the intersection of AI and semiconductors. She's based in London. She brings decades of experience unpacking the world of chips, systems, and smart machines, with a knack of making complex tech both accessible and insightful. And she's been covered in a lot of top-tier publications and holds a master's in electronic engineering from the University of Cambridge. Ian was actually the former senior editor at Tech, and now runs More Than More, as well as the popular YouTube channel Tech Potato, where he again breaks down a lot of detailed hardware, CPUs, infrastructure, and has a growing global audience. With a PhD in physics and a reputation for sharp data-driven analysis, Ian has over 100,000 YouTube subscribers to his channels. Okay, so with that, right, I'd like to get started to the meat of the show. Anything to say before we start? Sally, Ian?
Thanks for the wonderful introduction. Yeah, let's get on with it.
All right. So I think what I thought would be useful is to kind of take in, on this show, we've covered Keith Wittick, we've covered Roshan Shankar, we've covered Raja Kaduri. A lot of tech evangelists and leaders were building inside out, if you will, but with a clear view of the market. And you guys have had the advantage of looking at it from the outside in. So my first discussion on this would be really about how you see AI, and we'll kind of weave that in from edge to cloud. So for Edge AI, I guess I'll start with you, Sally. It'd be good for us to understand, firstly, what is edge, what's an endpoint, what's sensor edge, and a little bit more about what's driving growth and innovation at the edge.
Yeah, absolutely. I guess it depends how you define edge, whether it's the telco edge, whether it's an edge server somewhere in an industrial factory aggregating data streams, or whether it's an edge server maybe in a retail application looking at a camera stream from the security cameras, right down to through cars, all the way through every kind of appliance or device, consumer devices, right down to the sensor edge, which is more like, industrial predictive maintenance and so on. So talking about everything from server kind of power draw right down to really, really tiny sensor edge, which is microwatts. So we cover an awful lot in the edge spectrum. I think, with the exception of the sensor edge, probably the biggest thing driving edge AI right now, is focused on is the LLM trend and the open source LLM trend. I think everything is going to get an LLM user interface. All kinds of devices are going to get this LLM powered user interface, and it's a matter of trying to fit that LLM into the compute and memory and power requirements that you have in an edge device. That's probably the biggest thing, the biggest driver right now pushing this kind of technology.
And do you see some of the comments around SLMs or structured state-space models or things that are pushing that down making a big difference, or is it still really a battle of getting the hardware more efficient rather than much more compact models?
So it's definitely a little bit of both. You mentioned state space models there. To me, that's more on the neuromorphic end of things, like at the really tiny power budget end of things. But at that end, I feel like you definitely need more specialized hardware. So I kind of put that group on its own. In the mid-range, in the sort of few watt range, do we necessarily need specialized hardware for LLM? I'm not sure. But yeah, again, this is a thing at the edges. There are so many different niches, so many different technologies, so many different applications. It's like there's room for all of these technologies to exist side by side.
That makes sense. And actually, one of the twists we added for this show is we actually started a post on LinkedIn that was taking polls for a few topics, and we'll touch on them. And clearly, Edge AI is one of the interesting and what should I say, topic with a lot of different types of views. Now, moving to I would say, network edge and cloud. Clearly, foundational models have been driving it. Generative AI has been driving it. But what is now, in your view, Ian, shaping AI infrastructure and hyperscaler and cloud deployments?
You can think about it in two holistic views, right? You can talk about it in the way of enabling the future AI and the go-to-market strategy, or just simply the what is possible strategy. And realistically, the thing that's driving both is just in depth and amount of compute you can put into one place at one time. That's efficient and connected together. We're seeing gigawatts of build out from the hyperscalers, from large companies just wanting to get a grip on large foundational models, being able to build out just their I want to say a database of data, but that's a really confusing way of putting things. They just want to make sure they have the best models such that when it does come filter down, when they do additional factors such as fine-tuning, agentic workflows, that they're starting from the best base possible. And the way to get to the best base possible is to have the most data, the most compute, and the most time. That's why there's such a run on everything relating to high-performance compute, infrastructure design, whether that's networking chip to chip or system to system, or even certain circumstances, data center to data center. How quickly can you create 100,000 GPU, 1 million GPU? And then the big question mark over what's happening in China, where power is cheap, space is cheap, but compute may be behind. Can you simply get over that with scale? So for as many different functionalities and modalities we talk about in edge, cloud and data center does sometimes feel like a lump. But the more you spend looking into it, the more nuance there is in everybody's desire. And we can touch on sovereign, all these sorts of other different implementations of cloud and all the players there. But the growth is happening, and as we're recording this, we've just come out of financial season. Everybody's numbers seem to be going up, and bigger bar better, right?
Indeed. I think the the consistent discussion about scale out and now scale up, and now we talk about scale within NISC. Our good friend Carl Freund talked about, but generally scale is the constant comment, and each of that is pushing up. So one of the things you mentioned about data center to data center, system to system, rack to rack, etc., which brings us to the first of our polls, right? So really, what is driving the AI bottleneck today, and what is the chance to fix it? I promise this poll wasn't set up to be self-serving for biosystems, but clearly most of the respondents seem to think data movement and memory is the key issue. So let's start with that. I'll start with Ian this time. What do you think?
It's data movement and memory being the highest result here at 55%. I think when I saw this poll a few hours after it had gone live, we had almost 100 responses. So it's clear there's a lot of industry who are thinking about where exactly the data has to go in that infrastructure. One of the key metrics that we always look at when it comes to AI is hardware utilization, right? This idea of you've just spent 80,000, $250,000, couple of million on chip, server, rack. How much work are you getting out of it? Where's the bottleneck? Where's the limiting factor? And realistically, even in good training today, and even in a number of inference applications, when your big green GPU is only utilized 30%, are you getting your money's worth? And the reason why that's a bottleneck is simply usually down to data movement between the chips, whether that's chip to memory, chip to chip, server to server, and again, rack to rack. The number of companies that Sally and I track and cover, I want to say perhaps about 55% of them are trying to solve the data movement and memory scenario by trying to improve that utilization, either through tips, tricks, either by doing what we already know better, or by trying to approach it from a very different degree of freedom. I saw this poll and I actually voted for people. Right? There's been a long-standing discussion, especially in the United States, about the capability of semiconductor expertise, of software engineers, how new jobs relating to machine learning and chip design are cropping up all over the place, and machine learning is reinvigorating the market, not in terms of interest, but in terms of how you learn to become an expert in the field. And that's not really properly thought out yet on the global stage of what's best practice. So everybody's trying to find their own way. And in a sense, that's a bottleneck I see again and again and again and again. You can't solve for data movement without having people, right? So how far up and down the stack of that argument you want to go? I don't know. What do you think, Sally?
Yeah, I think for edge, data movement and memory bandwidth utilization, absolutely key themes. More like at the silicon level for edge than at the networking and rack level. But I mean, some of the ways we try and tackle this at the edge are near memory compute, in-memory compute, where we mix compute and memory together with some level of granularity to try and keep the data right next to the compute where we need it, to try and avoid bottlenecks like that. We also have schemes like compute in memory, so analog compute, basically doing the compute in the memory, which is another way to try and keep the data in one place, so we don't need to move it around and try and avoid that bottleneck a little bit. Yeah, I mean, when I saw this poll, I voted for software optimization. It's the one I voted for. I mean, all of these are a bottleneck. All of these are a problem. I voted for software thinking, because I was thinking about, when workloads first come and first emerge, and first they run on NVIDIA, on big GPUs, And then what happens is on the same hardware, NVIDIA or the NVIDIA ecosystem innovates very strongly on software. People write new CUDA libraries and people tweak it and, really go for it on the software side. And the difference that can make is absolutely huge. So yeah, I don't know if that 11% there is me, if I'm the only one that voted for software optimization, but that was my thinking of where the bottleneck is, one of the biggest bottlenecks today.
Well, so some people would say it's power efficiency, and it wasn't an option. And I highlight this because Sally and we recently recorded one of our own episodes where we're talking about companies that are dropping out of AI, whose play was power efficiency. And it turns out because of the scale issue, power efficiency's lower down the priority list in terms of having to solve that problem, even though so many companies today we speak to are all about the power efficiency. I mean, Sally listed off so many architectures that are power efficiency focused, so to speak. So,
yeah, I mean, that was a bit of a surprise. It seems obvious from the outside that surely everybody needs power efficiency. Data center needs power efficiency. They obviously have a power footprint that they can't go beyond, and everybody at the edge needs power efficiency. So, yeah, it's a little counterintuitive to see some of these companies fail where power efficiency was their main benefit.
No, indeed. I think, from my past life at ARM as well as what I see here, right? We think about compute, we think about power efficiency, but in general, often it's taken into account on a widget level rather than a holistic system level. And AI is all about data. And so if data movement is where the bottlenecks are and the inefficiencies are, and in order to scale, you need to solve that problem. I think that's probably where the dissonance comes from, even though it's technically not a dissonance, right? And you all know Jim Davies. He used to run the ML group at ARM. He'd pretty much say it's finally about data movement, right? And the more efficient you make, especially AI, deal with data, the less you have to reuse, and more reuse and less movement there is, the better efficiency you get and the better performance you get. It's kind of a virtuous circle. So I think that brings me to a question that you've been kind of dancing around a little bit, right? So obviously this means it's not a CPU type model or a GPU type model, NPU type model. This is really about how do you make computation very close to where the data is or minimize the amount of data that is moving. So is the industry kind of getting the hype around computation right versus kind of thinking about it as an intelligent distributed computing system? Right? We've always seemed to look at hype around the compute companies and UNPUs, etc. Whereas it's really about the broader data movement and system or data processing system that goes around. Is that an interesting view, or is that just me being a little bit outside in?
Yeah, I don't know. I think in terms of whether compute is overhyped versus innovation in interconnect, I think it's obviously you need both.
Yes.
You need to solve all of these bottlenecks, which is basically, Amdahl's law. You have to improve every part of the system to get an overall speed up. So yeah, absolutely, we need to innovate in all of these layers. How easy is it to innovate in interconnect versus compute? I'm not sure. So some of these will come faster than others, I think.
From my perspective, if we just look at memory being the bottleneck full stop, right? You either take a top-down or a bottom-up approach. So your top-down is improve your networking, improve your infrastructure, improve your chip-to-chip. So, this means more HBM, more memory bandwidth, more, moving from copper to optical and trying to solve that sort of situation. Whereas the bottom-up is simply, are we doing the right mathematics? Is the software optimized for the hardware? Is the algorithm being optimized for the hardware, or is the hardware being optimized for the algorithm? Right? We're seeing a lot of again, companies in this space approach it from either direction. Where you think whether the benefit should be a top-down or a bottom-up approach, or even where there's value in the market when you discuss the differences between the two. One argument is the bottom-up approach requires a full redesign of the infrastructure anyway, whereas the top-down, where you replace the infrastructure with faster networking, is just a simple drop-in replacement, but doesn't solve any of the underlying inefficiencies in the architecture itself. But it's great to see that there are so many people thinking and trying to solve it on both sides. Our good friend Jim Keller, CEO of Tenstorrent, he whenever you ask him, how's this going to be solved, how's that going to be solved, if it's not anything he's working on, his answer is just simply, it'll be done, there's smart people on it. He trusts the industry, which is a good place to be.
So hence the people vote from you.
Yes.
But also, I think I completely agree. It's not one or the other in all of this. This is really about thinking somewhat holistic, but also looking at local optimizations, bringing that up. So it's kind of a top to bottom and bottom to top approach. Which brings me to my next question on this, which is really about chiplets and modularity, right? How do you actually see this evolving with maybe best in breed combining for scale or optimized for fit for purpose solutions?
Yes, I mean, at the edge, chiplets is in embedded something we've always done. We just used to call it something else, system and package. So I think chiplets for AI in the embedded space are going to bring some of the same benefits, which is this modularity, which means you can create custom solutions and custom system and package easier for the niches that you want to go into and make that more economical. But you can also do, let's say you had analog compute and memory, you could use an analog process node for that compute chiplet and then have memory on something else. And it kind of helps you to optimize the cost of the design. I mean, yeah, these are all embedded themes, and chiplets definitely plays into those.
Cool. So I think with that setup, Sally, I'll go to our second poll, which was intentionally a little bit provocative on is Edge AI real? Is it already here? And I know where I voted, but I'll let you start with that in mind.
So I voted already here. Because I know that my smartphone has been doing a number of AI tasks on its CPU for a lot of years. They just maybe didn't call it that, or maybe consumers not aware of that, doing these bits of recommendation and so on that happen on phone. I think it's already here. I think it's already here when you have Alexa. I have Alexa in my house to control certain aspects of my home setup. We've been using that for several years. It works pretty well. It's already here. I already have AI in my washing machine. A Samsung washing machine that has AI in it. Exactly what that does, I don't know. But there it is. It's here. It's already here. So anybody saying it's all hype, I think they just got their head in the sand, I'm afraid.
So I certainly voted there as well, because both in my past two lives, if you will, with smartphones, Alexa, and then the third one with what we're working with companies like BrainChip, where AI is even making it at the sensor edge. Obviously, there it becomes more specialized, and how it engages is different. But clearly, it's there. I think the question is scale. But if you were to kind of pick out a couple of your key use cases that you feel have changed way things are done at the edge over the last couple of years.
The key use cases kind of at the far edge are stuff like wearables, earbuds, what smartwatches. We need to do a certain amount of AI in those, whether it's like recognizing heartbeat, recognizing wake words in really, really tiny packages. That one's definitely changing. Another one I think is really important is, and I'm sorry if people think this is boring, but industrial predictive maintenance that uses AI algorithms to tell when the machines need maintenance, which is absolutely huge and can save, I don't know if it saves trillions of dollars, but it's a very, very large application. That's something that's been revolutionized by AI at the edge. So yeah, those are probably the two key ones for the endpoint right now.
Yeah, I think I would agree. I think the numbers were about $50 billion annually just in the US for predictive maintenance. That's quite, I mean, the savings from predictive maintenance. So I think I've heard bigger numbers as well, but one of them was kind of a backwards looking proof, which seemed pretty cool. All right. So now we've talked about the edge. We've talked about edge AI's actually here, but are we in a space where the models, I mean, are getting too large or useful outside of hyperscalers? Obviously, there was a lot of buzz around DeepSeek earlier in the year. So Ian, I mean, obviously, you've been monitoring this very closely. How would you see this going?
Well, I think it comes back to our first poll, really. Is this software innovation? Is this people innovation? Our good friends over at SemiAnalysis have shown that if you want a GPT-3 equivalent model today, GPT-3 at this point is just over 2 years old. I think they're actually announcing GPT-5 today as we're filming this, that sort of thing. You can now get it for, say, 1,200 times cheaper than it was at launch, just because you can now get the same benchmark quality machine learning answers from a 1.2 billion parameter model rather than a 560 billion parameter model or whatever they had at the time. That's partly just due to how we optimize the data, how we make sure we're using good data and not trash data, supervised learning, then going beyond to mixture of experts and some of these highlighted points that DeepSeek put into the wild, and the step functions. Yeah, obviously on the flip side, to your point, GPT-5 coming out today, that's going to be how many trillion parameters, how many mixture of experts? We had Llama 4 a couple of months ago. Everybody wants, the best base for these models, and that's going to obviously stay in a situation where in order to keep that model alive, you need terabytes, if not petabytes of storage or HBM in certain circumstances. Going back to the connectivity question, the memory and the memory question, in the past, people just bought 8-way racks of servers just for more HBM in their compute. They didn't actually buy it for the compute; they bought it for the HBM. So you're spending $250,000 just for 480 gigabytes of HBM, and that's changing. The question is whether that's a wave that's actually going to iterate down. I know you use the context of LLMs and SLMs as an opportunity to explain the scale. In my mind, it's all LLMs because it's all token in, token out, and how we optimize for that. I am seeing companies who are able to do hyper optimized 8 billion, 40 billion parameter models, but the way they monetize it is differently. Usually we see monetization of those models in sort of dollars per million tokens, input, output. They're doing it as part of as a different service. And the AI is built into the service, so they can then go charge, instead of $10 per million tokens, the equivalent of 2,000, because the use case of those models in the infrastructure they're providing for their clients, the value's in not just the model, it's the wrapper you put around it, it's the way it's used. So the economics are going to change with these large language models as well. But for the peak top, yeah, we said it a couple of years ago, right? There's only going to be a half dozen companies that can even build them, let alone just run them.
So I think that's an interesting spot, and I'll ask Sally for input shortly. But I think that from a scale perspective and innovation perspective, which is what our poll 3 was, right? clearly, NVIDIA has been at the forefront of driving the platforms, the software optimizations, just the size of the ecosystem. Going forward, do you still see that as still the main driver, or is it beginning to move, and it needs to move for the both the sustainability, the cost, the different regional needs for it to change?
I voted for startups with custom silicon because I want to believe that's true. But hearing your intro there, I'm like, yeah, it is NVIDIA, isn't it? Like, it is NVIDIA. It's NVIDIA because they are deployed at such scale. It's like any small innovation that they make has an outsized effect, right?
It's I want to say that this question, people saw it and said, who do you hope will be the next driver of AI innovation? And of course, it comes with custom silicon. It comes with open source communities, and that's where people hope it's going to be. And I think part of that is just simply NVIDIA's been quite open with their roadmap, right? Mm-hmm. They've told everybody where they're going. They're told everybody how it's going to be delivered. I mean, it's the pickaxe seller, right? They're going to sell the pickaxes, and you can use the pickaxe for whatever you want, whether that's an AI factory, whether that's a training system, whether that's Stargate or what have you. And that's obviously going to come on leaps and bounds because NVIDIA's hiring more people. I think in the last year they hired another 20% headcount, on another 8,000, I think, in their fiscal year reporting last quarter. So their software team's bigger than most companies' full AI stack teams. So of course they're going to innovate. But one question overriding that is this carrot, is this stick, right? Are they going to be defining their own boundaries? I mean, Sally and I have talked about this before, how if you go to NVIDIA research, there's tons of ideas that are floating around, some of which they might tell you about. Right. But it turns out there are other custom silicon companies in the space who already have had those ideas and are going to market with their solution in that space, kind of not necessarily blocking NVIDIA out, but trying to put the patents in place to make sure that NVIDIA can't encroach on their ecosystem. Will that drive a next wave? NVIDIA thought about it, but also so did these really smart people. It's tracking revenue numbers over the next 5 years is going to be exciting in terms of number, but maybe depressing in terms of direction. Unless you're an NVIDIA stock.
I'm sure all of us have some level of stake in there. But so let me kind of switch it a little bit, right? So you can see the transition that ARM's making, for example, and creating both a chiplet architecture for scale. It's also very prolific in its penetration across different markets. You're seeing RISC-V companies trying to band together or create an open system as well. And I know I'm saying CPU architecture, but it's about a heterogeneous or intelligent compute system to support it, and software ecosystems that go along with it. What would it take for those things to really drive AI? Maybe on the edge, you're already seeing where the prevalence of smartphones, MCUs, you can see ARM kind of doing that. Does that actually help with kind of near edge and cloud as well?
I want to say what would drive that is cheaper leading edge manufacturing. You touched upon, say, like the open chiplet ecosystem before, and the advent of chiplets. Very few companies are looking at a catalog of chiplets and picking and choosing what they want from it from different vendors. Most of the chiplet-based systems we've seen in the cloud today, with the exception of HBM, because that's a traditional commodity market, so to speak, everybody's either building their chiplets in-house or doing super tight integration with a third party that they just somehow eventually acquire anyway. So the open chiplet ecosystem, all the standards around that as well. The idea is that yes, there's this laminated catalog of dreams where you can pick and choose, you want this compute, this memory, this analog, this what have you, that you can put on a PCIe card or an OEM module and then ship. The reality is the manufacturing is complex, the packaging is complex and expensive. And then you've got to test and validate. You've got to do known good die. You've got to, can you do testing while it's not packaged or pre-packaged? And there's an ecosystem around that as well. On top of that, leading edge nodes are expensive, and getting even more expensive. And in the cloud, in the data center, you have to be on N or N-1, sometimes N-2 if you're lucky, to be able to compete in that space in order to even get 0.1% of the market, which is soon going to be billions of dollars, right? So I sound downbeat on enabling that. I hope that there is an easy way to do this. Samsung Foundries, for example, their SF4 node looks like it's going to be used by a lot of people and can drive down costs. A lot of users of TSMC N5 and N3. N3 is getting expensive. But yeah, no, we're seeing a lot of players who are also trying to tackle the supply chain issues of some of those things as well.
Yeah, I think and the idea of a chiplet marketplace, right? There are plenty of challenges still to be solved, interoperability being one. But really, I think we had this discussion at a panel about a month ago where really it's who's going to take the indemnity of if something fails from different vendors, who takes the hit. So some of those things are maybe logistical or underwriting / liability more than purely technical, right? So there are business challenges to be solved as well. Now, I think we're getting towards the end of our session. We've been having a lot of fun. So I'll make the fourth poll question. I think I know the answer based on the previous one, right? But are we nearing the end of the GPU era? It's probably a fait accompli based on previous, but also I think it'd be useful, especially in kind of to define what GPU past meant versus where it is now.
I'm going to say I hate the distinction that people make between GPU and anything else. One story is that I was working with a company who I tried to convince them to call their architecture the acronym GPU, just to leverage the fact that investors can't seem to tell the difference. But they decided not to go down that route. But even Jensen seems, not too fussed about GPU as a term for any of this. Realistically, all the chips we talk about are some form of application-specific architecture with some flexibility. You could argue where they fit on the CPU to ASIC scale. So in this instance, are GPUs, as in the ASICs provided by NVIDIA and AMD, still the best option? I would like, part of me wants to say they're never the best option, but they might be the only option that's available at scale with enough software support, right? And in that case, they're the best option, not because of the hardware, but because of the ecosystem, right? And that ecosystem has an incredibly high bar for anybody to come along and revolutionize the entire market space. If you've got a niche, for example, our good friends at Cerebras have a niche with their wafer scale design, and that's seeing traction in very specific markets because it's not just 10% better, it's order of magnitude better. And ultimately, that's the way that a lot of different hardware companies in this space have to take it. You have to be an order of magnitude better, in more than one degree of freedom if you can, and have the software nous to even get into a micro market and at the end of the day build revenue.
Anything to add to there, Sally?
So Yes, because I think we are not really considering the edge with this. Already at the edge, we don't use GPUs. In embedded devices, we don't use GPUs for AI already. That transition is CPU to ASIC. We're not really considering putting an NVIDIA GPU in something like a smartphone to do AI, or in an appliance, a home appliance, or anything smaller than that. So yeah, I think in that case, GPU definitely isn't the best option. What is going to be the best option is going to be very much more varied landscape of different things coming from different angles for different niches. And it's just the same as what Ian said about the niches. You have to really tackle that niche really well and be very, very much better than the existing solution to win it. But I think in the edge, that transition is already happening.
So, okay, Sally, I'll put this to you. ARM has Mali, right? They have micro NPU for ultra low power, but they've never gone down the route of having their own AI architecture, right? For sort of what scale edge, right? Their argument being, if you need AI, use the CPU, use the GPU, or if you're a client and you have your own AI device, put it on there. So why is ARM not tackling this market in the same way? And they're saying use our GPU.
Are they saying use our GPU? I think they're saying use our CPU. Certainly at the tiny end, they're like, oh, here's ARM Helium, and then here's the micro NPU for sure. I don't know that maybe I'm wrong, that they necessarily market Mali for AI workloads beyond a bit that's already related to graphics. Should ARM make an NPU that is a bit bigger? That's a whole other podcast that we could do. They don't. So obviously they see the reason. I think they see themselves more as, I'm sure you have an insight into this, Nandan, as well, but I think they see themselves more as taking the CPU side of it. In the data center CPUs are all going to be ARM, they think, or they hope. And they put their embedded cores next to other AI accelerators, and that's where they see their role right now. But yeah, what they will do in the future, who knows?
They just, acquisitions by SoftBank.
Yeah, just a little hint about what might be to come. Yeah.
So yeah, I think I would not speculate on this. That's probably, as you say, it's a whole new topic, and all of us have history there. Clearly, there is still a lot of innovation going on at semiconductor chip level, right? And data movement is critical. We're seeing that, but also there's this top-down view of let's understand what we're trying to build before we build it. How can we do it on a single die with all these different compute engines? How's the software going to fit into the ecosystem? All of these challenges, everybody seems to be going at from different directions. But the common themes I see are that AI acceleration and specialized acceleration is still building in a lot of pockets, right? And they are pretty decent sized pockets that are not as general purpose for the rest of the AI. They're within data center. You're seeing a lot of networking infrastructure, which has always had specialized ASICs also start doing that. Automotive, where people want to maintain some of their data, are very, very particularly keen on secrecy, are doing that. And of course, at the network edge, and especially in different regional areas, we see a lot of innovation with different types of compute engines connected up into large-scale units, on die, across die, multi-die, and then of course systems. Clearly, what is common theme across this is how do we design, right? For new semiconductor designs, I think there's a design paradigm change. The idea that IP can be delivered as chiplet, and the path towards that, all of that seems to come together as where a lot of the investment's going, which is, I think, good for the industry. But before we wrap up, I also wanted to touch a bit on your upcoming TV series or TV-style video series. You want to give us a little bit of a teaser on that?
So if you're listening to this and you're interested in AI chip companies and the complete landscape of AI chip startups out there, as well as what's happening from the major players, Intel, NVIDIA, AMD, and all the big ones too. Ian and I have a video podcast that we do with filming season 2 right now, so that'll be airing pretty soon, where we talk about all these different chips and chip companies and what makes them unique and special.
It's our first season we did a couple of years ago. We did 12 episodes, 72 different chips. We had over 1 million viewers over the course of the season. Very well received. I'm surprised how well received it was, because for the most part, it's me and Sally just talking about how we feel about these companies, right? How they've interacted with us, what exposure they're given, but also the opportunity where they sit in the marketplace. It's really fun just to speak to somebody who's both smart and incredibly like-minded about a lot of this industry, because we're both speaking to the same people, but we get such different information a lot of the time. So it's really great to share that with an audience who are really interested in AI hardware.
Yeah, I think if you want us to disagree, that doesn't always happen on the podcast. It's more like we're both ranting in the same direction because mostly we agree. But yeah, hopefully it'll be interesting and informative and fun too.
First episode should be coming out early September, and then one a week each through to the end of the year.
Sounds good. And so then to wrap up from each of you, do you have one word that jumps out at you to describe the future of AI systems? Sally first.
I was going to go with brain-like. I discounted suggestions like ubiquitous. I was thinking from an edge perspective, but yeah, I think the future is definitely more brain-like, whether that's analog or spiking or more neuromorphic type of ideas. So yeah, brain-like.
Okay. How about you, Ian?
Cost. I mean, I track so much money in the investment sphere going into a lot of these startups, and it's almost in line with what the big companies pay individually in terms of their R&D as well. There's just so much money floating about because the potential, especially the potential for agentic workflows and inference, is that by the end of the decade, it's going to be 90% of the revenue in machine learning. So yeah, cost.
Both of you, thanks for coming on our podcast. This is actually our first video one, so big start there. Looking forward to your upcoming video podcasts, and again, thanks for doing what you're doing. Keep looking forward to what you guys are going to present both in the podcast and in your respective channels.
Thank you very much.
Thanks, Nandan. Thanks for having us on the show.
Thank you for listening to Tech Threads, Weaving the Intelligent Future podcast. Join us monthly for insights into the evolving tech landscape and the future of chiplet technology. If you enjoyed today's episode, don't forget to subscribe and share it with your network, and stay tuned for more expert discussions. Let's weave the intelligent future together.